for the mechanical components in transport vehicles to achieve the high fuel efficiency. And at the same time, the steel, it has the high absolute strength and high reliability. So in the mechanical components in the transport vehicles, the aluminum alloy and the steel are both required in the same structure. So it's very important to establish the welding technique of the dissimilar weld between the aluminum alloy and the steel. And fusion welding is a kind of conventional welding method. However, it easily forms intermediate compounds because it melts the materials and due to the difference of the solidification temperatures. And the intermediate compounds are essentially brittle. So it should be avoided. The FSW is a solid phase welding using a rotating tool which causes friction heat and makes plastic flow easy in the solid state. And FSW doesn't melt the materials, so FSW is regarded as advantageous in dissimilar welds because the formation of brittle intermediate components is suppressed. However, in the FSW, the brittle intermediate compounds remain. And to know the basic properties of the intermediate compounds of dissimilar FSW joints is important in engineering. And the aim of the current study is to examine how to evaluate the fatigue crack propagation behavior in the intermediate compounds in the interface of the aluminum and steel dissimilar friction style weld, and to evaluate them. The materials used in our studies were the aluminum alloy 60616 heat-treated plate with a thickness of 6 mm and type 304 stainless steel plate with a thickness of 5 mm. And the chemical composition and mechanical properties shown in these tables. This is the illustration, the very simple illustration of the FSW, but I skip the explanation of the FSW principle itself. And this is the friction style welding tool that we have used in our study. The material of this tool is SKD61 Japanese industrial standard steel, which is a worldwide standard H13 high hot work tool steel. And even though it is made of hard steel, if you put the tool in the steel side, then the tool is severely worn out. So in our studies, we avoid to put it in the steel side, we just put it in the aluminum side. And this is the appearance of the welded joint. As you see, the weld zone is formed in the aluminum side. And this is how we sample specimens. This is a configuration of tensile specimen. This is configuration of CT specimen, which were used for the fatigue crack propagation test. And as you see, the specimens is a sample with the center lines aligned with the interfaces of the joint. And to avoid the possibility that the specimen includes the welding defects, we sample the specimen from the center in the thickness direction. Before we conducted a fatigue crack propagation test to find out the appropriate condition, we did the tensile test with different welding conditions. And we have changed the rotating speed, the offset, which means the distance between the interface and the surface of the tool pin. And we set the traveling speed constant at 100 mm per minute. And this is a map of the tensile strengths, depending on the welding conditions. And as you see, that the highest strength was achieved with the 800 RPM and offset of 0.2 mm. And this is the hardness profile in the cross section of the joint. As you see, the hardness increased in the steel side near the interface. We think that this is due to the work hardening effect. And as you see in the aluminum side, the hardness decreased. It is due to the resolution of the precipitates because this material was heat treated beforehand. And this is a macroscopic appearance after the tensile test. And as you see, the fracture occurred at the area where the hardness decreased. And as you can easily imagine from the tensile test, the crack might propagate in not along the interface, but it might deviate in the aluminum side because the hardness of the aluminum side is decreased. And so, to avoid this deviation and to let the crack propagate along the interface, we did the heat treatment again to increase and recover the hardness. So we prepared two different samples for the crack propagation test of the dissimilar welds. And for the comparison, we also prepared another sample of the aluminum alloy. And this is a test condition, the frequency of 10 Hz and the stress ratio of 0.05. This is the appearance of the crack path. As I have explained, in the as welded joint, the crack didn't propagate along the interface. It deviated into the aluminum side because the aluminum side is softened by the heat generation, by the friction. And after the post-heat treatment, the crack propagated along the interface. So hereafter, I'm going to talk about the comparison between the heat-treated sample and the aluminum basic sample. We relate about the FCP rate with respect to the crack singularity parameter. We used the very standard CT test specimen, and in this specimen, usually the stress intensity is calculated using this approximation equation. However, in the so-called bi-materials with different elastic moduli, the stress intensity becomes quite complex, and the stress intensity cannot be calculated using this equation. This is just the graph which shows the crack propagation rate with respect to nominal stress intensity factor range. However, as I explained before, as I explained now, the stress field becomes complex in the interfacial crack, and the stress singularities of not only mode 1 but also the shear mode 2 appear. So this equation, this approximation cannot be used. There are several ways to calculate the stress singularities in the interfacial crack. Here we first calculated the stress field near the crack tip using a commercial FEM called Nastran, and after we calculated the stress field by the extrapolation method, we calculated the stress intensity factors in the mode 1 and mode 2 respectively with respect to the crack length. And after that, even though after the calculation, just the interfacial mode 1 and mode 2 stress intensity factors, that those values cannot be directly compared with the single material's stress intensity. So we calculated the energy release rate by using the interfacial stress intensity factors. And now we can evaluate the crack growth rate with respect to the energy release rate. This is the equation that we have used in our study. It is as you see in this equation, you have to use a so-called bimaterial parameter and some other parameters, the material constant. And this is a comparison. This is a result of our test about the comparison between the dissimilar welding joints and the aluminum alloy. And here you can see that near the threshold area or in the low delta G region, the crack propagation rate in the dissimilar welds and the aluminum alloy itself are comparable, not so different from each other. But in the middle range of delta G, a crack propagation rate in the dissimilar welds become a little bit higher than the aluminum alloy, and after that, it fractured in greater manner. So the brittleness, the fracture toughness of the intermediate compounds in the interface in the dissimilar joint is quite lower than the aluminum alloy itself. Here I can show you the detail of the deviation point. As you see, it deviated from the interface at this point with a degree of 9 degrees, and there are three cases which can be imagined, which can be considered. But here in this study, we see the crack propagation in the interface and the deviation into the aluminum side. And we consider that this crack path can be determined by some kind of criteria, such as using the fracture mechanics parameter, such as biomaterial parameter, not only by the biomaterial parameter, but microstructures such as the hardness with grain size are also important in this case. But I think I do not have enough time to explain the detail about this one, and so I hope you to look at our future paper. Yes, now I show the conclusion of this study. In this study, we did the crack propagation test in the dissimilar aluminum steel FSW joints, and we evaluated the crack propagation rate using the energy release rate, and we found these conclusions. Thank you.